All right, today we are looking at limiting reactants, and so we're back to the cheese sandwich recipe that we started out the unit with. We've got, again, our 2 slices of bread and 3 pieces of cheese is how we make one sandwich. And so we've actually seen the 2 parts of this problem that I have up on the screen here, but how many sandwiches can be made out of a loaf of bread and a half a pound of cheese. So we've already talked before that 18 ounces is the loaf of bread mass or weight. There's 1.5 ounces per slice. So if you divide those two, that means that you've got 12 slices of bread to work with. The pound of cheese contains 30 slices, so if we only have a half pound, then that means we've got 15 slices of cheese to work with. And so the thing to keep in mind with a problem like this is that we're given the amounts of both of the ingredients. So I need bread, I need cheese, and I need 2 pieces of bread per sandwich, 3 pieces of cheese per sandwich. So from the bread that I have available, I can actually make, again, if there's 12 slices of bread, 2-to-1 ratio for bread to sandwiches, and so I can make 6 sandwiches with that amount of bread. For the cheese, if I have 15 slices, then for 3 pieces of cheese, again, it's a 3-to-1 ratio for cheese to sandwich, so I can make 5 sandwiches. So that means then that I am limited by the cheese. So the cheese is going to limit me to being able to make 5 sandwiches. Again, the bread, I could have made a 6th sandwich, however, I run out of cheese beforehand, so I'm going to have leftover bread. And so this problem then leads us into what a limiting reactant is. And so one of the reactants, usually you don't have an exact amount to use up both of the reactants. So one of the reactants is usually going to be what's going to limit you to how much product you can actually make. And so in this case, it was the cheese. We ran out of cheese after we made 5 sandwiches. And so again, the answer to the question of how many sandwiches can you make is determined by those numbers of cheese, by the number of cheese pieces. Again, in theory, with the bread that was available, I could make 6 sandwiches, but ran out of cheese before that was possible. So I have 2 pieces of bread left over after I've made the 5 sandwiches. So we're doing the same exact thing when we deal with chemistry problems. The difference will be that, obviously we're working with grams or moles or, volume of solution or whatever. But the thing to keep in mind, the parallel with this example, is that we're going to be doing 2 sets of calculations. So unlike the problems that we started off the unit with, where you were given an amount of one substance and then you were kind of told, oh, you've got plenty of the other, or don't worry about the other. In these problems, you're given amounts of 2 reactants, and that's how you know it's a limiting reactant problem. So you're essentially doing 2 parallel calculations when you have a limiting reactant problem, and then you're looking at which one of those gives you the smaller amount of product, and then that's going to be the answer to your question of how much product could be made. All right, so we're going to look at the worksheet D that you're going to be doing, and this goes back to that water reaction. So 2H2 plus O2 yields 2H2O. So that's the balanced equation we see here at the top. And just to work through one of these examples with you so that you know what you're supposed to be doing. So for this, we're supposed to be counting up the molecules here, and each molecule is supposed to be representing 1 mole of the substance. So this is H2, so there's 1, 2, 3, 4, 5, 6. So there are 6 molecules of H2 here. And so I'm going to write that down, 6 moles of H2. Obviously, you will write it smaller and more neatly, but this is all I have available to mark this down right now. For oxygen, 1, 2, 3, so that is 3 moles of O2. And so then in looking at, again, they combine in a 2-to-1 ratio. So I have exactly enough, so I have 6 of these and 3 of these. I have exactly enough to make 6 moles of water. So what you're going to do is draw. So you'll need to go back and draw this on your own paper. So you're writing out the example. So again, each of these splits up and pairs up with one of these O's. So you have 6 water molecules. And just to show you what this looks like, again, 6 H2s and 3 O2s. Notice there are 6 water molecules. So in this case, I don't have any leftovers, right? I have exactly the right amount. It's a 2-to-1 ratio. I have 6 to 3, which reduces down to 2-to-1. And so I'm able to make 6 water molecules because every one of these combines with one of the reds, and that gives us a water. And so that's going to happen 6 times. So you're going to draw the 6 water molecules, make them look like this. And the O's are bigger and the H's are smaller. And then you're going to do the other one, number 2, underneath that. So let's look back at the worksheet. Actually, just to show you the math setup, just like we've been doing on the other worksheets, I can figure that out this way. So, using the mole to mole ratio conversion factor that we talked about. So it's 6 times 2 over 2, that gives me 6 moles of water, and 3 times 2 over 1 gives me 6 moles of water. So this is, again, the mathematical way that you can set it up and check it as you're doing the rest of the sheet. All right, so let's go down to this. So you should read the background information before you actually do this. And then we're essentially going to be doing the same calculations, except you need to make sure you check both of the reactant amounts. So let's see what that looks like. 1, 2, 3, 4, 5, 6. I've got 6 hydrogens again. And this time I've got 1, 2, 3, 4 oxygens. So in order to figure out how much water can be produced, I need to figure out how much water could 6 moles of hydrogen make, how much water could 4 moles of oxygen make, and then figure out, again, which of those is going to produce the smaller amount of water. So, again, looking at the calculations, there they are. So for 6 moles of H2, we already did this one before, so that can make 6 moles of water. For 4 moles of oxygen, that's 1 more than what we had for the last problem. So this can make, actually I would be able to make 8 moles of water if I had enough hydrogen. However, I only have 6 moles of hydrogen, so that means then that I'm going to be limited to 6 moles of water. So notice I did 2 separate calculations, and so that means then that I can only make 6 moles of water. So that's what you're going to draw in your picture here. So 6 molecules of water. And so the limiting reactant, so I'm limited by the hydrogen. So that's the thing that I'm going to run out of. Oops. So I'm limited by the hydrogen. Why is this giving me a hard time? Limited by the hydrogen. There we go. And so the excess reactant is the other one, the oxygen. So I'm not running out of that. All right, so then let's look at what's left over. Well, go to the simulation and see. Notice the difference here. So 6 H2s, 4 O2s, I get the 6 molecules of water. And again, there's an extra molecule of water that could have been used to make 2 more waters. There's an extra molecule of oxygen. Did I say that? But that gets left over. There's not enough hydrogen. We're out of hydrogen. And so I have 1 molecule of oxygen left over. So that's what we're going to record on our sheet. So I've got 1 mole of oxygen left over. Now, if you want to figure out, like, if you don't have the pictures in the future, because that's eventually what we want to wean ourselves off of, I could do the calculation for figuring out how many moles of oxygen would be required to react with this. So, again, if I wasn't sure how to figure that out, I could set this up. So for 6 moles of hydrogen, if I want to figure out how many moles of oxygen would that react with, it reacts in a 1-to-2 ratio, so I would need 3 moles of oxygen, or I would end up reacting that with 6 moles of oxygen. So you can always go back and do these calculations to figure out what you need to figure out. So I'm going to do that for the rest of the sheet. You are supposed to draw the excess as well. And the whole idea with this visual is so that you can count up the atoms. So, we want to practice doing this visually, but we also then want to be able to do it via calculation setup. But this is supposed to kind of cement the concept in as to what we're doing. So you can do the rest of this sheet, and then we're going to take a look at what this is going to translate to in terms of real problems. So move down to here. All right. So when one of the reactants in the reaction runs out, the reaction is going to stop. That is going to be the limiting reactant, so it limits how much product can be made. So again, the example we just looked at, hydrogen was the limiting reactant. We ran out of hydrogen and we had leftover oxygen. And so again, when we look at how many water molecules we were able to draw in our picture, we were only able to draw 6. So how I know that hydrogen is a limiting reactant is that it limited me to the amount of product that I figured out. And again, you can look back at the 2 calculations I did, and whichever calculation gives me the smaller amount of product being formed, that's how I know the reactant amount that gave me that, that's the limiting reactant. All right, so for solving problems with limiting reactants, how am I going to know that I've got one of these? Well, there's going to be 2 reactant amounts given. There could be more if there's a reaction that has more than 2 reactants, but you're given at least 2 reactant amounts. So all of our problems in stoichiometry already have had here's a reactant, find this amount of something else, or here's a product, find this amount of something else. So there's already been mentions of 2 different things In this one, we're going to be given two different numbers to start with. So that's the thing to look out for to get you going on setting up the double problem. So to determine the limiting reactant, you're going to find out which reactant makes the least amount of product. And here's just an example. So 95 grams of nitrogen gas is reacted with 45 grams of hydrogen gas. And there's the balanced equation. And then we're asked to determine the limiting reactant, find the mass of ammonia that will be produced. So we're going to be doing two separate calculations. You're not adding up the nitrogen and the hydrogen, because we didn't do that with like our bread and cheese example. It's like I took the bread and figured out how many sandwiches. I took the cheese and figured out how many sandwiches. So that's what I'm going to do with this. I'm going to take the 95 grams of nitrogen. How much ammonia could I produce with that? 45 grams of hydrogen. How much ammonia could I produce with that? And then I'm going to compare. So first thing, identify the given information and what you're solving for. So that's what I'm looking for. So I'm going from grams to grams. And notice, again, numbers for N2 and H2 and looking for NH3. So this is a limiting reactant problem. So we're using the given information to convert to moles since I don't already have moles. And now more than ever, it's really important to label which thing is which so that you know, like, oh, these are the amounts that go with nitrogen, and I'm converting that to ammonia, and these are the amounts that go with hydrogen, I'm converting it to ammonia. So if you don't keep that separate, things can get very messy. And I know I'm going to be breaking this down step by step and doing these two kind of simultaneous calculations. I would normally do these line by line, like I would do the nitrogen all out to ammonia, and then do the hydrogen all out and then to ammonia. So there's the converting to moles, and I'm going to do that for both of these. And again, you can pause at any given point in time to try the calculations yourself, and I strongly recommend that. So find moles if you don't already have moles. Second thing is, well, now I need to convert to the type of mole I'm interested in. So I'm trying to find out about ammonia. So there's my mole-to-mole ratio for ammonia. There's my mole-to-mole ratio for ammonia from hydrogen. And at this point, even without doing the final step, which is find the mass of ammonia, you can already see that the 6.78 moles of ammonia, my last step is going to be to multiply by the molar mass of ammonia. And obviously 6.78 being a smaller number times a molar mass for ammonia, which is 17, is going to be the smaller of the two masses. So right off the bat, I can kind of save myself a little bit of work that this one's going to be producing the smaller amount of ammonia. And so that means then that it's nitrogen. Nitrogen is the reactant that's giving me this smaller amount of ammonia. So you would not circle the 6.78 moles of ammonia and say, this is your limiting reactant. This is the amount of ammonia, the moles of ammonia that are produced. The limiting reactant is a reactant, so it has to be on the left side of the equation. So the nitrogen amount, the nitrogen is the one that gave me the smaller amount of ammonia. So nitrogen is the limiting reactant. I'm able to produce 6.78 moles of ammonia. And so then lastly, to answer the question, I convert that to grams. And so I found it's 115 grams. Make sure you answer the question. So I was asked to find the amount of ammonia formed and the limiting reactant. Again, you could find the grams of ammonia from the hydrogen number, but it's going to be a bigger number, and that is not your answer because you are not going to be able to make that much. Once you get to 115 grams, all of your nitrogen is going to be used up, and that's it. So that's limiting reactant problems in a nutshell. So again, you're doing two parallel calculations, but just exactly the same way that we've been doing before. So you take each number for each reactant that you're given, solve it out to the product amount, compare, and then whichever gives you the smaller number is your answer to the question of how much product is produced. The limiting reactant is the reactant that gave you that smaller number.